Yeah. Okay, so I'm starting today's session by introducing myself. I am Moinak Ghoshal. I am a PMRF at ISAR Kolkata, and I have been assigned as the TA for this course, which is entitled as Application of Spectroscopic Method in Molecular Structure Determination, where we discuss about some spectroscopic method which will be helpful for you to analyze your compound spectra, and from this spectra you can easily tell about what kind of composition or what kind of bond property is there in your molecule. And this is questions regarding assignment of week number 5, where I am going to discuss some questions regarding that. Uh, but before going to the questions, I would like to discuss something that is already discussed by Professor Sankaraman. Very well, this was discussed. In the previous session, we have talked about we have solved some questions regarding NMR, where regarding NMR and where 1H NMR and 13H NMR, 13C NMR data was given, and from that, if you need to interpret your spectra, and from the spectra you will be able and you need to find out which compound it is. So today's session is going to be a little more informative, and you need to find this structural information from your mass data. Also your mass data will be given. You will be given your 1H NMR, your 13C NMR data, and from then you need to find which molecular structure is corresponds to this data. Now, in the previous day, whenever we have discussed about mass spectra, we have seen that two types of mass spectra. One is EI, that is electron ionization or electron impact ionization. Another is chemical ionization, that is CI. Both of these actually produces a lot of fragments. From these fragments, if you are able to identify the fragments, then you will be able to tell that which kind of molecule it is. But this is very applicable for low molecular weight compounds, because the fragments actually is not possible for high molecular compound. We have also discussed that. So for when you are getting the fragments, so you cannot predict theoretically just after seeing the structure that these are the possible fragments. You cannot predict. By looking the fragment, you can predict the structure. The opposite is possible. Okay. So there are some techniques, soft ionization technique, in which fragments do not produce. Okay. And these techniques were not very much old, and these are very new techniques, and these names are given as ESI and multi. Okay, so ESI and multi, electrospray ionization and matrix assisted laser desorption ionization. Okay, these two techniques are very soft ionization technique, because it does not produce any kind of fragments kind of thing, and you can measure a large molecular weight compounds using this ESI and multi spectrometry setup. So here, unlike other mass spectrometric instruments where you need some vacuum from which your ionization will take place, here ionization actually takes place from normal atmospheric pressure. You have seen that. So what I have told, that these are soft ionization techniques. They are normally used for analysis of non-volatile, large, and often polar molecules. Okay, these non-volatile things was the limitation of CI. Whenever I have discussed about the CI, I have told you that the compounds would be relatively volatile. But if you have some non-volatile sample or some large molecule, like just like protein or more big biomolecules, for them your CI or EI, it's not efficient, because it will, if it creates fragments, the fragments will be large in number. You will be not be able to solve all these fragments. So you, in that case, you need to use this ESI-MS and ESI and multi. So whatever I told you, that proteins, lipids, and other molecules and other large synthetic molecules that are present, that can be detected using these spectroscopic techniques, spectrometry techniques. Now, there are mechanisms of ionization in ESI method. One is charge residue model, another is ion evaporation model. They actually are the complementary to each other, you would say, because they also say the same thing in a different manner. Okay, so charge residue model actually tells you that the solvent molecule actually goes with your ion of interest, and they actually get lower in size, and then at the final point of time, whenever your solvent molecule is completely evaporated, you will left with only the ion. The same thing ion evaporation method tells that whenever you are in the solvents actually, whenever the solvents actually removes or dissolve your ions that is present here, and you will get this from the large and you will get small ions. So the same thing is told in two different methods. One is charge residue model and another is ion evaporation model. You can see here whatever I have told you, that it is the ion evaporation model, that this is just going out, leaving out the solvent. And this CRM, that is charge residue model, here your large molecule is getting divided into small droplets. This is again which is called dotted droplets also, and this is also divided into small droplet. And finally, when the last molecule of the solvent evaporates, you will left with only the charge. So there is some techniques for sample preparation in ESIMS. Yeah, this one. So you need to flow your sample from here, and which is actually have some nebulizer like in the dry nitrogen gas will pass through there. Okay, here you can see. And now from here we'll see this what will happen. It will actually cure your droplets, and these droplets actually the solvent will be vaporized if this goes through this nitrogen chamber. Okay, so this process will be continuous, and you will be ended with some fragments or some ions which will have some charge, and this will be detected in your mass by charge ratio. And from there, if you know what is the charge, there is some formula to calculate this, what is this charge, and from that, if you know this charge, you can know the same. And hence the detection of this non-volatile solvent using ESIMS becomes possible. Now, one thing that you need to calculate when molecular weight from ESIMS, that I have told you about, that how to calculate this molecular weight from ESIMS. So you need to assign all the peaks. Suppose you have got one peak. Okay, you've got some peaks here like this. So suppose you got this n charged, it is n plus 1 charged. Okay, so this is explained by Professor Sankararaman. Suppose this is n charged, this is n plus 1 charged. So you just put this m by z value, and from there, just pick the position, you will get, you will know that what is the z. From this z, you will be able to calculate what is your m. Now, there are proteins that show difference in the ESIMS for native and unfolded state. Okay, because ESIMS actually deals with what is the charged state of the protein, and if it is in a native state, protein's native state means protein is already folded. Okay, so very much less atom sites are available for the protein to have this proton. Okay, but in unfolded state, very much amount of sites are open for the proton to couple with the protein. Hence, in native state, you will see low m by z values, but in unfolded state, you will see large n by z value. From there, you can differentiate between whether this protein is in a native state or in an unfolded state. Now, spots on the TLC plates can also be analyzed using ESIMS. Okay, so I'm not going into the detail here, but if you have this TLC, if you know this TLC, where you just need to monitor that how your sample is separating, and then if you just move the tip of the ESIMS, the ESI, if you move the tip over the TLC plate like this, and if you just remove these solvent molecules from there and just solute molecules and analyte is interested, then from that you will get the mass, and from mass you can differentiate between two compounds, because two compounds which you are going to separate in a TLC, they have different mass. Okay, so using this mass spectrometry, you will be able to separate these compounds. Okay, next, matrix that is used in multi. So there are some characteristics of a good multi matrix. What should be the characteristics? So it will not evaporate. Okay, first of all, if it is getting evaporated, then your solvent will be left there. so that will be not of any use. Another thing is it will, it will, if in multi, people generally use laser. Okay, so you need to have some absorption over UV region so that molecule can absorb and it can ionize your molecule of interest that you want to measure. Okay, and then the basic principle of time of flight mass analyzer. Okay, so there is only one basic thing about this, that this actually depends on one only basic thing, that lighter molecule moves slower. Sorry, sorry, lighter molecule move faster. So if you have a very molecule which has low mass, lighter molecules means it has low molecular mass. Okay, so if it has low molecular mass, it will move faster. If it is a high molecular mass, it will move slower. So from the time it takes to go from one way to another, you will get the velocity, and this velocity will give you kinetic energy, and from this kinetic energy and equating it with the potential energy, we will get the m by z value, and from this m by z value, we will be able to tell that a molecular ion is there, which is showing your molecular weight like this. Okay, so these are the things that Professor Shankar Raman has discussed with you in this module. And now I am going to some questions. But going to this week's assignment questions, I can remember that I have given you one assignment question to answer in the previous week, which I will discuss today. So first I am going to that, and then I will go to this week's assignment. So I gave you this assignment question where you need to systematically deduce the structure of the inorganic compound from the given data. You have given the molecular formula, and you have given this 1H NMR data of 12.2 ppm. One is 7.10. It has a DQ, which I have explained as doublet of quartet. Okay, and then I have given 13 NMR data also. So from there, you need to find out which structure is this or which molecule is this. So can anybody got this answer?
I have tried, sir.
Yeah, what is the answer?
So is it crotonic acid?
That crotonic acid. Anybody else? Anybody else? Okay. So I'm going to solve this problem. Let's see whether it is jet protonic acid or not. So you have the molecule C4H6O2. So you need to find your dBe as the rule suggests. So what is your dBe? 4 minus 6 by 2 plus 1. So your dB is nothing but 2. 4 plus 1 3. 6 by 2 is 3. Sorry, 4 plus 1 is 5. And 6 by 3 is 3. So it is 2. So there are two double bonded equivalent kind of system that is present in the molecule. Now you see the data that 12.2 ppm, there is a singlet of one hydrogen, which is very much chance that in 12.2 ppm only one group is there, which actually gives your NMR. Mainly this is acid group, carboxylic acid, 12.2 ppm, and here you see only one proton is there. So you can expect that this proton is coupled to no further proton, so it will give you singlet. And since there is two oxygen atoms here, so it will be very much desilted. Okay, so it will give your 12.2 ppm, which is one hydrogen singlet. Okay, so now we are left with three data of 7.10, 5.86, 1.92. From there, you just see that from this coupling constant they are given. So this one and this one is coupled. This is coupled to this one also because this coupling 6.9, and another thing is 1.6 is there in this one. Yeah. So from this you can see that three coupling constants that are given. So one is, I'm writing this coupling constant. This will give you some information about which kind of compound it is. Coupling constant J equals to 15, J equals to 6.9, and J equals to 1.6. So this actually corresponds to which kind of coupling? Transcoupling.
Trans.
Yeah. This corresponds to cis coupling. And what is this one? 1.6. This is nothing but geminal coupling. So this, from these three, will be, you are able to guess that one hydrogen is trans to other, this is cis to another, or this is gem to another. Okay, so this is only possible if you have come alkyne kind of system. Why? Because if you consider this hydrogen, this is cis to this, sorry, this is geminal to this one, cis to this one, trans to this one, and this is applicable for all the other protons if available here or here or here. Okay, so in this alkyne kind of system, this is possible that you have a proton which is cis to one and trans to one, and also geminal to one. Now if alkyne is there, so we are, there is one, yeah, somebody saying something. So in acid we have lost one carbon, two carbons we have lost in ethylene or this alkyne kind of thing. Okay, this is nothing but C double bond C, right? Now we have left with one carbon. Okay, we have used two oxygen, right, and one hydrogen, so we are left with CH5 kind of thing, right? Okay, I am just solving it from the backward, going by one, then we will be able to guess that what kind of compound it is. Now this CH5, you can see, now you go to your NMR number of protons. One is, there is one hydrogen, there is one hydrogen, another there is three hydrogen. So most probably one hydrogen, there is another hydrogen, and there is three hydrogen. Three hydrogen cannot stay here like this, so the carbon may be taken up by this three hydrogen. Okay, so you have completed all the molecular formula. This is done. Now you need to put these groups. Okay, so you have two hydrogens are there, methyl is there, and acid group is there. Okay, so first I am going to put some carboxylic acid. So you have four groups, you need to put it at the perfect place so that this satisfies the data. Yeah. Suppose I am posing it here. Okay, you can put it anywhere because this is carboxylic acid, you are first putting it. Now, one hydrogen, two hydrogens are you have. So you can see this one hydrogen things, this is trans to one hydrogen, and also this is, you can see here, this is cis to one hydrogen. Okay, so how it is possible? And this three hydrogen thing, you can see here, this three hydrogen doublet of doublet, this thing is cis one and geminal one. So since it is coupling geminal to any hydrogen, so I am putting it like this up to now. Okay, so you can see this is a three hydrogen, So you are left with 2 hydrogens. You have no other option, but you have to put it first here. Okay. Another option is that so which one among these? So these two structures are possible now. Now I need to find which one is the actual correct structure. So how can you find that? It's very easy to find it. Okay. So if this is the structure, you see these two hydrogens, these two 1 hydrogens, they are coupled via trans coupling. Here they are coupled via cis coupling. Now you need to see your 1H data. This 1 hydrogen, this peak, you see this is 15 hertz and this is 15.6 hertz. That is the same thing. So you can see these two hydrogens, that 1 hydrogen thing, they are have the same coupling constant. Okay. So this same coupling constant indicates that these two hydrogens are actually trans coupled. They are coupled trans. Okay. So only possible structure is this one. Okay. So you can see this one is a possible structure, which is known as, right, this trans crotonic acid. Now we need to follow the patterns. So this hydrogen, it will be 1 hydrogen singlet. These 3 hydrogens, what will be this pattern? This will be quartet because there is not hydrogen here. So sorry, this is 3 hydrogen and there is a hydrogen here, so this will be doublet. Then it will couple with this one, so it will be doublet of doublet. Similarly, this one, this hydrogen, there is in this carbon there is no hydrogen, but it will couple with this one. Okay, so it will be doublet, and this the methyl group, then it will couple with this methyl group, and this will be quartet. Doublet of quartet. Similar for this one, so it will not couple like this. Here is no hydrogen, so it will couple with this one. This will be doublet, and for this methyl, it will be doublet of the quartet. So I have matched all the proton signals that is present in the molecule. Now I need to match this carbon 13 in our data. So 172 ppm, which one will be this one? Who told me that you have done it?
Carbonyl carbon, sir.
Which one?
Carbonyl carbon, acid carbon.
Acid carbon, yeah. This will be 172. Now, which should be 147 and which should be 122? This I know in 19. Yeah. Tell me which one will be 147 and which one will be 122? This one will be how much? This one will be how much?
122.
Which one? Right one, left one?
Right one is near carbonyl carbon. It is 147,
Mm-hmm.
and another carbon is 122.
Everybody agrees? Everybody agrees to that? Everybody agrees to that?
Sir, I just wanted to have how you have the coupling of geminal in this molecule which has been suggested.
Geminal coupling with this methyl, right? Coupling will be very, very weak. The methyl is there.
So, geminal between proton and the CH3 group.
Mm-hmm. Yeah.
Sir, carbon near to carbon will be less ppm value than the carbon away from the carbon.
Okay, I am just naming it. Okay, this is 1, suppose this is 2. C1 and C2. Which one will be 147? C1 or C2? Who is chilling? Okay, so whoever told me, I don't know her name. Q1 is 147 and sorry, Q1 is told 22. This is 147. Right? But if I would say that it will be reversed. Any logic? I'm saying this carbon has higher delta value. This carbon will have higher delta value, delta higher compared to the other carbon. This carbon. Okay. So any logic? You just see. Yeah.
Conjugation.
Conjugation. What will happen?
Sir, resonance. Resonance will be there, sir.
What is
Carbon 1 bearing a negative charge.
one by one? Please one by one. Carbon 1 bearing a negative charge.
Negative charge. And this
Remote
bond shifted towards and we get O minus.
one was this one. Yeah, correct. Anybody else?
Carbon 1 has positive charge due to resonance
Why?
with the carbonyl oxygen.
Yes. It will have delta plus charge because this kind of compounds is known as alpha beta unsaturated compound. Okay. If you have run their Michael Addison reaction, you will see that this is alpha beta kind of unsaturated compound to a carbonyl, and this charge, this position is very much attacked by a nucleophile. So this is very electrophilic position. Okay. So this position, since it is electrophilic, so there will be very less electron density. Since there will be very less electron density, it will be more decelerate. So it will have higher delta value. You will see it will have a delta value of 147. Okay. Similarly, for 2 C2, the delta value will be 119. 122. Okay. Okay. So this is the answer. And whoever have done this jet protonic acid, you are absolutely right. Done well. Very good. Okay. Now I'm going to questions regarding this week's assignment, which will be discussed, and this is actually dealing with some questions where there will be given the spectral data related to mass spectrometry, and you need to identify the fragments also, that which fragments are giving this kind of data. Okay. And if you will be able to give this information, you will be able to get this structures. Okay. So in somewhere proton NMR data is always given, mass data is somewhere given and somewhere not given, and carbon data is given, I think, in one or two questions there. Okay. So let's start with question number 1. Yeah. So you need to identify the structure of the compound from the given data, and you have to interpret the data to the structure and arrive at. Okay. So you are given. Okay. Let me read one. Yeah. So you have C9 H12 SO3, and in NMR you are given two data of 7.8 and 7.4, and it will following A prime BB prime pattern of 4 hydrogen. Also there is a 4.1 quartet 2 hydrogen, and this coupling constant is same. Always look at the coupling constant. This is same as this one, and this is showing 3 hydrogen triplet. Okay, and this is 2.5 singlet 3 hydrogen. And in ESIMS, you will go to ESIMS later after just completing from this NMR. Then we will go to this ESIMS. But first, from the NMR, can you predict what kind of compound is this?
Para substituted.
Yeah, first of all, it's para substituted. Then Now
Now
One ethyl group,
SO2,
CH3, CH2.
OCH2 CH3, then SO2 CH3,
H2
methyl group,
SO2
SO2 CH.
SO2 CH3.
Yes, sir. SO2 CH3, then
This one you are talking about?
OCH2 CH3,
Only
OCH2
both CH3.
CH3, CH2
Mhm,
CH3.
mhm. SO2 CH3.
No, yes, sir.
Anybody else? Okay, let me go one by one. First, you need to find dB. dB is nothing but how much it will be? 9 minus 12 by
For
2,
what, sir?
4. 4. So there is 4 double bond or equivalent kind of system that is present here. Okay. Now you need to see here that from this data, first you know this is a double bond, or paradise substituted compound. Yes, it's correct. And you will see the values are 7.8 and 7.4. I will put the value last. So singlet 2.5 3 hydrogen, what could be possible? Before going that, I'd like to tell you that you see a 3 hydrogen triplet and 2 hydrogen quartet. I told you the same thing. This is nothing but ethyl group. CH2, CH3, right? So there is some methyl group there, and now you need to analyze when this one 2.5 singlet 3 hydrogen, you will see this singlet 3 hydrogen is nothing but presence of methyl. Generally, methyls appears generally at 1 point very low value. Okay. So this one, this methyl, toluene methyl, you will see this toluene methyl also shows like this. Okay, this 2.35 kind of thing. So there is a chance that this is the methyl group which is attached to the compound, right? And whatever you are left with here, you have done C6H4 plus CH3 is done. You know you have some ethyl group CH2 CH3. You just add up all these things and they see how many carbons you are left with. 6, 7, 8, 9 plus 4, 3, 7, 2, 9, 3, 12. C9H12, it is done, right? Now the same thing, if your ethyl is attached and you see you see this CH2 CH3 one, in this for this CH2 you see this has very high value, so it is attached to any electronegative atom, and since this value is very high, which is very much signifies that it is attached to very high electronegative atom, this is nothing but oxygen it is attached to it. Okay, so it is attached with nothing but oxygen, it cannot attach with sulfur. Now you are left with just SO2. You just put it here. Now where to put it? Okay. Now why I am predicting this one? Why this one is not correct? Whoever have told it, this is absolutely. You see the patterns. This is absolutely correct. Then why I am predicting this one? So how to know which one is this? Is this the correct structure or the left one is right one? How do you know?
By mass.
Yeah. So here the main thing comes that you need to do mass. Okay. And you know this group SO2 group, if you do mass, this is very easy to leave. SO2 kind of thing, this thing. That means this bond fragmentation is very easy. Okay. So in mass spectrum, if you are going to record mass, there will some time come when your SOS group will get removed. Okay. Similarly, so if for the future purpose, I am thinking that this group is removed. So where am I left with? I am left with is someone like this, right? And if same thing I think here, this SO2CH3 is completely removed, I will left with like this. Right? Now you just need to find which fragment you find in your mass data, right? That fragment you find in your mass data is your compound. So you see this one actually giving these CH3 bonds. This one C6, C7, 8, 3, 4, 5, 6, 7, C7, E7 plus. So okay. So generally toluene, if it is present, I will come into that. So this generally gives a peak of 91, but this is not toluene. This is something else, which I will talk about after just this question. So you see there is a peak at 91. You see here. Okay. So if toluene was not there, so what should be the another one? This is 16, 16, 12 is 30. So you need 121 kind of peak. You will not see any kind of 121 peak. So you are confirmed that this could be your possible structure. But you know to also verify your other structures. Okay. So I am just getting this structure. Okay, this methyl and this S double bond O CH2 kind of thing. Now from NMR you just got this all this data. Now you need to assign all the peaks. I have told you this methyl protons is 2.5. You have got all these data. So this is nothing but 2.5, right? 2.5 is yeah. This methyl, this is nothing but what is given? 1.3. This ethyl is 4.1. Here are hydrogens. Okay. There is another hydrogen. Okay, so the another side is just equivalent, it's like this. Okay, so among these two, you are left with only two values. One is what is this? Yeah, 7.8, and then another is 7.4. You can now easily predict which one is 7.3, which one is 7.4. So if I name it HA, yeah. Now if I name it HA and this I name it HB, so HA will be which one? 7.8 or 7.4? And HB will be which one? Which one will be HA? This one.
7.4
Which one?
HA.
HA 7.4. Why 7.4 HA? I guess. So chemical shift actually depends upon where in nearby you have any electronegative atom. So among HA and HP, nearby to which one hydrogen you have the electronegative atom? HA or HP? You have electronegative atom sulfur, which is very close by. Sorry, you have electronegative atom sulfur, which is very close by to HP, right? So HP will have higher chemical shift value, and this will have lower chemical shift value. Okay. So I have explained the NMR spectrum of this kind of compound. Now I need to match it with your mass spectrum. One fragment I have got, the other fragments I need to pull. Yes. Yes.
Sir, your voice is breaking and not audible.
Can you hear me? Hello.
Yes, sir.
Now it's okay.
Okay. Now it's okay. Yeah. Okay. Uh, so we have the compound. So I have the compound. This one. This is methyl. What was there? Sulfur. Double bond oxygen. Double bond oxygen. O H2. Right. Okay. So calculate its molecular weight. You need to know how much molecular weight is given. C9H12SO3. C9H12SO3. So C9 means 12 into 9, 108 plus 12, 32, 16, 48. So you calculate it, you will get 200. This is the base peak. Okay, first I like to write the base peaks. 200, 172, 155, 200, 172, 155, 107, 91, 65. These 6 fragments I need to explain. So you got 200 is the molecular ion peak. That is the main peak for this compound. Now you see 172. Another peak is there of 172. What it should be? You see 72 is nothing but if you lose 28 molecular weight, right? So 28 molecular weight is very much possible to lose if you have this fragment is how much? 15. This is 14. So 29. So you have a 28. So very much chance that this is reduced, this is broken, and will end up like this. You calculate it, how much it will be. You have leap, see, you can easily calculate 15 and this is 14. So 29 is gone, and if 1 each is there, so it is 28. So one from 200 to 28, it is nothing but 172. Good. Another thing, you can easily break this one also, right? Why I am taking it? Because you can see next one is 155, that is loss of 17. Now from here 17 loss is possible only if you have an oxygen which is 16 and one hydrogen 17. So one fragment could be like this. SO4. Okay. So one fragment will be like this, and it is losing this one. So this one is a charge, and it is 155. Right. Now, what I have told, it's now coming to that. This is easily breaking. This SO2 is released. Now I am living with this one. Okay. How much it is? It is 91. So in general cases, now what I'm just going to tell, just listen carefully. In general cases where you have any benzylic cation type of thing, benzylic cation type means you have this one, this CH2 kind of thing. Suppose here is a positive charge, okay. Here is a positive charge. If this is the case, is generally it goes to tropylium ion. What is tropylium ion? Tropylium ion is a 7-member ring. 1, 2, 3, 4, 5, 6, another is 7. So this is tropylium ion. There is a positive charge, and this is delocalized over the ring, which will look like this one. Okay, and this generally gives peak at 91. So in case of any compound, if you have any kind of alkyl group or it adds to the benzene or aromatic moiety, and if you have come up with like this, and you have seen come up like this, and if you have seen that in mass spectra you got a high peak at 91 m by z value, and also it is generally associated with this one 65, it is likely that this is lost, 2 higher carbons is lost from given carbon. This is a 7 carbon ring, right? This C7 H7 plus. So whenever you are getting this 91 peak, you should not write this there. This is due to this methyl and this toluene plus. Okay, this is due to this propylium ion. Okay. Now, whenever you are going through this propylium ion, you have seen this 91 peak is there. There is another chance that 2 carbon will be lost as ethylene. There is a loss of ethylene, and then you will be able to see a 5 carbon species like this. Okay. So this is nothing but cyclopentadienyl cation. Okay. So this will have m by z at about 65. And some cases also, if you leave another 2 carbon, you will end up with cyclopropane ring. Okay, only 3 of them will be there. So you will get to see that also that fragment, but that is very less generally observed. Generally, these 2 are mainly observed: the tropylium cation and the cyclopentadienyl cation. Okay. So here you see 172 peak I have explained, 155 I have explained, 107, this is only left. So how 107 could be possible? 107 was there? Yeah, 10% of abundance. How would be possible 107? Okay, so I have this one 155 one. Okay, now you see this, if you add 16 over here, there is a chance that it will be 107, right? So this is highly possible that in some cases your OH dot that is lost here, if this oxygen is attached to here. Okay, otherwise it is not possible. You cannot say which fragment is this without knowing this one. Okay, this is the only possible thing from which you will get 107 peak. That is, if oxygen that is lost in this one, this OH, this oxygen is attached to it. Okay, and this has very low abundance of about 10% or something. So there is very lowest chance, but this is the only possible that oxygen is attached to this. So these are all the fragments that are possible in this compound. So any kind of benzylic ring, if you see, if you see a 91 peak, another 61, 65 M/Z peak, you are definitely sure that there is a chance of this one, this benzylic.
So I have two doubt.
Okay.
You mentioned about 107. Where will be the positive charge here for this 107?
Yeah, that's a good question. Actually, what happened? It will be say this here. This is minus. Yeah, that's a good thing. I need to check it. Okay, yeah, that's a good finding. Good. Another one?
I'm not clear with the fragmentation which you got as 172, because the actual mass which has been leaving this particular whole molecule is 29.
Mm-hmm.
CS2 and CS3 ethyl group goes as 29. But when you check out the difference between the molecular mass and the fragment 172, it goes as 28.
Yes, right.
I'm not clear with when the mass is leaving as 29 and we got the actual decrease is 28 and we get at 172.
Why not? It's not possible. Because this is the bond is cleaving, okay? It is homolytic cleavage, so it will radical to the radical.
Is it fragmentation or rearrangement?
No, this is fragmentation, not rearrangement. Rearrangement means this molecule, this group will migrate from one place to another. This is rearrangement, but this is not within the molecule. It is leaving it. So it is
But
not a rearrangement.
how we are getting that H from then to this SO3 group?
Why not? Because this is CH2 CH3. This will train to form CH2 CH2 ethylene. Okay.
Goes a neutral molecule ethylene.
Yeah. Why not? It's a very good chance. So one hydrogen will be H dot will be lost, and it has a high chance of forming ethylene. So if it is a chance to stabilize, so it will get stabilized. And this H dot will be accepted by this one. Okay.
So we have to mention that if it is the loss of 28 is accountable for the loss of neutral molecule. Neutral fragment.
Okay, so the molecule that is lost, actually you don't need to show that. Okay, so
Okay.
the fragment what you is responsible for this one, you need to show that. Okay.
Okay. Okay. Thank you.
And another, this question is very good question. So I should look at this 107 fragment.
Thank you, sir.
Thank you. Okay.
Sir,
Yeah.
172,
Mhm.
172, is this a radical cation or a simple cation or radical? What is it?
It's a radical kind of thing.
Okay, sir. And
Okay,
can
so
you
cation
please
is not here.
explain again? Yes, sir.
Which one? Which one?
I have a doubt. The original
No.
molecule you got at 200. There was another possibility too. That is OCH2CH3 and SO2 group will be at the para position. And why you eliminate this?
Which one? Last
How
one.
did you eliminate the?
This one?
Yes, sir. How did you eliminate that? Yes.
Okay, so if you have this, suppose these two are my options. Okay, so at some point of time you are seeing there is a loss of this group. Okay, so this carbon sulfur bond, this will be clipped, and you will left with this one, right? And if this is the possible structure, if this bond is clipped, you will left with this one, right? So if you measure this mass, you measure this mass and see which mass is you are getting in your EIMS data. Okay, the mass you are getting in your EIMS, that will be a structure. You are seeing you are getting the 191 kind of thing. Okay, and here you will not get, you think it comes like a 120 kind of thing. So you cannot get any kind of that kind of peak. So you just remove this one because this cannot be possible, because if it is possible, then breaking of the CS bond will give you this structure and you will give a peak corresponding to this in the EIMS. But here you are giving 91 peak, so this is your corresponding is possible structure. You got it?
Okay, sir. Got it. Thank you.
Now, next coming to the next question, the answer is written already. Okay, so EIMS of orthonitrile this shows here the molecular weight of 137. This shows a large fragment ion at M by Z of 120. Okay, orthonitrile you all know. Now the EIMS of alpha 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 trideuterio orthonitrile that does not show any peak at M by Z 120 but does have a peak at M by Z 122. You need to show the fragmentation pattern that accounts for this observation. Sorry. So what is your question? Your question is saying that your orthonitrile is which is drawn over here, this is a molecular weight of 137, but it does not show that much of intensity of this. Rather, you see maximum intensity for 120 M by Z. Okay, so you see only 17 molecular weight less. So you need to predict that what kind of molecular arrangement is going on, or what kind of fragmentation is going on here. Okay. Also, you have some more information that if it is deuterated, presence of alpha 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 trideuterio orthotoluene. Okay, so suppose I am drawing this. This is CD3. This is NO minus double bond O. Okay. Now from this one, you see you get M by Z equals to 122. What is the molecular weight of this compound? You just replacing 3 hydrogen with 3 deuterium and you will increase this 3. Okay, so it will be 140. Okay, so it will showing 18 less, right? So what could be the mechanism? So you need to find that, and you see the difference between these two peaks. Here it is 3 because 3 deuterium is present. You can guess that here this is molecular weight 137, here molecular weight is 140. Okay. Here molecular weight is 137 and his molecular weight is 140, and there is 3 difference because 3 hydrogens are replaced by 3 deuterium. Now you see in the mass spectrum there is a difference of 2. That means 2 hydrogen is replaced by 2 deuterium. Okay. Now you can get the idea that 3 hydrogens are not there. You get 2 hydrogen only. Okay. From there it is very much possible that 2 hydrogen is replaced by 2 deuterium, and you will get peak at 122. Now if you go to the mechanism, I am writing the structure in a little different way. So there is a chance that this will affect this hydrogen, this will give this one, this will leave this one. Okay. And since it is leaving this one, so it will left with OH. So okay. Now we calculate the molecular weight. C7 C7 H 1 2 3 4 6 NO. Let's see how much it is. So yeah, C7 1 2 3 4. I think I have counted correctly. 1 2 3 4 5 6 7. Hydrogen is 2 3 4 5 6. Yeah, NO. Yeah. So 7 is 84. Hydrogen is 6. Okay. Now you get this N. This is nothing but how much? 14. This is 16. So 90. Sorry, 90 is 50. How much is the sound? 90 is 14. So 84, 620, 90, and it is 120. Okay. You see 120 molecular and peak. This fragment is mostly responsive. Okay. Now we need to explain this 122 peak also, which is highly possible if you replace this hydrogen with deuterium. Okay, if your CD3 reacts like this one, just one deuterium is removed, so we will left with this one. Okay, so this is your most possible structure. So it will give you peak at 122. Got it? Okay. Now moving to the next question. All the structures I have given. Mass spectrum of a compound showed intense molecular peak at 1/772 and equally intense peak at m/z 174. One HNMR shows A prime BB prime pattern at a delta equal to 7.3 and 6.8, and also broad D2O exchangeable peak. And here carbon 13 data are given, so you have to need to identify the compound. Now see here you have not given, so don't look at the structure now. Okay, so here you are not given any kind of molecular formula that is highly possible. Rather, you are given that you have individuated 172 and another equally intense peak at 174. You know that whenever I discussed molecular mass spectrometry initially, that M and M plus 2, it is very possible that chlorine or bromine could be present in the molecule. Okay, so isotope peaks, that where we have told you that the presence of chlorine and bromine will always give M and M plus 2 peak due to presence of isotope. Now, whenever you are not given any kind of information about whether chlorine or bromine is present in the molecule, how do you know that chlorine is present or bromine is present from the data that mass it is given? How do you know that chlorine is present or bromine present? I have written here bromine present. How I know?
Their proportion 3:1 and 1:1.
Yes, exactly. If chlorine is present, the ratio of the peak position, you will see it will be 3:1. But if bromine is present, the ratio will be always 1:1 because the two isotopes of bromines are almost equally abundant in the nature. Okay. And since I am getting a M plus 2 peak, which indicates a halogen is present, now I am getting 1:1 ratio of these two peaks, which indicates that bromine is present. Okay. So first comes I come to a conclusion that bromine is present. Okay. Now I need to know that A prime B prime pattern at delta 7.3, 6.8 here, which indicates para disubstituted compound. So I am left with, suppose it is how much it is bromines, that will be good. Almost I took it almost 80. Okay. And now okay, so I take 171, 79, and this is nothing but C6H4 moiety, right? So 6 to 72, 76. Okay, if you add this up, 7, 7, 14, 15, no, it will be 155. Now look at your MI spectrum. You are left with only 17. And to get what is the 17 coming from, you have just one choice. You have just one choice that you need to see from here. Broad D2 exchangeable peak at 5.2 ppm. Okay. Now broad D2 exchangeable peak at 5.2 ppm, which is very highly possible that OH on NH2 is present. Right. So this one and this one, how in mass, terms of mass, how they are differing? How they differ in terms of mass? They differ.
Mass is even.
Yeah, 16. Their mass is 70, right? And you are left with 17 mass. So this is highly possible that this is the structure. Okay. So I have arrived that this is the structure. Now I need to assign the carbon peaks. Okay. The 4 carbon are there: 155, 133, 118, 113. So 155 one, which one will be 155 one? Which one will be 155 one?
Hello?
Yeah.
One was out oxygen.
Sorry.
Oxygen. The structure
The structure.
was out OH.
This one.
This one.
This is 155.
Yeah.
Yeah. 133. Which one this will be? It is 155 because it is at this carbon is attached to most electronegative atom in the molecule. Okay. Oxygen is the most electronegative atom. So next one will be least electronegative atom, then oxygen, and then only possibility is bromine. So this one will be 133. Now we need to find out which one will be 118 and which one will be 113. which one will be 118 and which one will be 113.
Are the
118,
hydrogen or what?
118.
Which one will be? Suppose I am
118 carbon attached with CO.
so I name it A
B.
and B. B will
B
be
is 118. 118.
and which one? B will be 13. Right?
Sir, what is the meaning of a DO2 exchangeable peaks?
Ah, okay. So I have explained that in the second or third lecture also. Okay, so I'm explaining you in short. So if this hydrogen, okay, so if you see NMR of any alcohol or in this kind of thing which contains this OH or NH2 kind of thing, there is a chance that this hydrogen is exchangeable with your molecule of solvent. Okay. So suppose for ethanol, you will see that the OH proton, whichever it will come in the NMR spectrum, you will see it will have a broad nature. Okay, why broad nature? Because this hydrogen cannot be easily detected because easily it is regularly interconverting with a solvent. Right now, D2O exchangeable means if you have D2O solvent, okay, water with water you cannot detect it.
Yes, sir.
Right, so it is
Yes,
so
sir.
fast you cannot even imagine. So how can you detect that if it is happening? You need to use D2O. What will happen? You will get something with OH and something we will get with OD. From there you will be able to say that whether this D2O's D is incorporating in the molecule or not. Right? So
Yes,
this
sir.
is called D2 exchangeabilizer. You got it?
Yes, sir.
Okay.
Thank you, sir.
Okay. So you have got all these answers for this one. Now I am going to the next question. Okay. So you need to deduce the structure of the organic compound from the given data, and you have to interpret the data to the structure you propose. So you have the molecular formula C9H10O2. C9H10O2. Mass spectra is given at first. Oh, okay. You just for some time you just close this mass spectra and you just see from this NMR if you will be able to predict it, and then you will match with the mass spectra. Okay. So C9H10O2. Okay, just give me 1 minute. I'll be back. Just give me 1 minute. Okay, sorry for the delay. Okay, coming to the question now. Yeah, so you need to reduce the structure of the compound from the data, and here you are given the molecular formula C9H10O2. Now, if you find double bond equivalence here, this is 9 minus 10 by 2 plus 1. So this is 5, 9, 16. So it will be 5. Yeah. So 5 double bond equivalence system is present in the molecule. Now, from the structure, can you predict which kind of compound is this?
Monosubstituted benzene.
How can you say that?
Because here we get 5 hydrogen giving a multiplets.
Exactly. 7.3 multiplet 5 hydrogen. This is very much indication that this is aromatic proton and 5 hydrogens are equivalent. They are giving like multiplet. So this is possible only if you see this kind of structure, monosubstituted benzene. So these 5 hydrogens are almost equivalent. Okay. Now, since there is nothing, so it is C6H5, and you have C9H10O. So how you are left with C3H5, right? So you see here you have 12.1 delta, a broad singlet of 1 hydrogen. What it could be? It could be
Acid.
acid, exactly, CO2H. So you have taken from here what is CO2H. So you are left with C2, O2 is gone, H is gone, so H4. So C2H4, the part is only left. You need to find out it. Okay. Now you see here what is left on your NMR data. You have 1 hydrogen and there is another 3 hydrogen, right? 1 hydrogen quartet, 3 hydrogen doublet. That means this is like this, right? This is 3 hydrogen doublet. This is 1 hydrogen quartet because 3 hydrogens are there. So 3 plus 1, 4. So this hydrogen will give 1 hydrogen quartet, and these 3 hydrogens, they will actually give 3 hydrogen doublet, right? Whatever you have seen, and these 2 hydrogens are coupling, have the same coupling constant, so they are coupled to each other. So all of these giving idea that this could be the molecule. See, all the NMR data are matching with it, that this could be the molecule of interest, right? So this hydrogen, these 5 will give multiplet, these hydrogen will give quartet, these 3 hydrogen will give doublet, and these hydrogen will be broad singlet. So you are done with your NMR data. Okay. So this is the compound what I am talking you about. So now you need to match your mass data. Okay. Now what should be the mass fragments that you are expecting? You see how many fragments are here? 5, 1, 2, 3, 4. Only 4 fragments. Okay, Prakash. Okay, fine. I will upload it today or most probably tomorrow in the YouTube. You can follow it. Okay. Now you are left with this C2H4 fragment. Going left. So we have reduced the formula. Now you need to see what is the fragments. So 150 most high molecular weight peak is mostly due to this molecular ion. Okay, so you calculate it. C9 H10 O2. This is 108. This is 10. This is 32. So 118 and 32 150. Right. Now you need to find 105. Which among these three will be? Which among these one will be 105? So from 150 to getting, yes,
Acidic group with remove 45.
acidic group
We
comes
get 105.
to the 32, 40, yes, 40, right. So you have got this loss of acid group. Okay. Okay. So loss of acid group is give you this peak, which is nothing at 105. Is this the correct structure? You see, check this molecular weight. This is 105. But what I'm asking, is this the correct structure?
It will rearrange.
Will rearrange. That's the same thing that I have told you in the last question, last or second last question, that if you have a benzylic cation, there is a high chance that there will be rearrangement and they will form cyclic toponium ion, toponium cation. Okay. So here there will now this will be CH3, right? So it will be delocalized over the ring. So it generally looks like 3, 1, 2, 3, 4, 5, 6, 7, like this, and this is methyl. You calculate this molecular weight. This is also 105. Okay, so I have just not changing. I have just making rearrangement, right? So this is 105 ring. Now, whatever. So you see how much is the difference. If in the previous case I have told you that the peak will be at 91, here you are seeing a peak at 105. So you see the 14 unit difference, right? Now you can easily tell that whenever I have told you that 91 peak we will get along with another peak at 65, now you are getting 105 peak. Here is another chance of getting this peak which is also present at 65 plus 40, right? Here the difference is 14. So you are getting a peak at a higher 14 M by Z bomb M by Z, which is 14 amounts higher from the previous one. Now this 5-membered ring, which is also possible for this 91 peak, you should expect something which is also a 14 units higher from this one because of this loss, CH2 loss. Okay, so you see here, if there is another peak is there at 79. Okay, so what is this could be? This could be this one. Okay, and the positive charge is delocalized over here, right? Now you say another peak is present at 77. The 77 peak, it's most likely this is due to loss of hydrogen. So H2 loss you can easily say. Okay. So if somebody can see it, okay, space left, right. Okay, I am drawing with a different color. Yeah. So this is this is 79. So if you remove H2 from here, this will form a double bond. So this will show your 77. So these are all the fragments for this molecule which you will see in this picture, and this is the compound. Okay, got it? Okay. Now coming to this question, you have to reduce. So you have to reduce the structure of the organic compound from the given data. You need to interpret the given data to the structure that you propose. The same thing. You will have given the molecular formula. Okay. C6 H14 O. Okay. So here you see double bond equivalence is 0, right? 6 plus 1 7, 14 by 2 7. So this is 0. So there is no double bond in the molecule. Now, if you are going to NMR, you see only just 2 peaks are there. 3.6 septate 2 hydrogen, and here 12 hydrogen doublet. Okay, and J is same. That means they are coupled to each other. How it is possible? So 0.9 12 hydrogen. If you see this molecule, your first thing comes into the mind, there could be 12 methyl groups which are equivalent. 12 methyl groups that are equivalent, right? This is the first guess that comes to your mind. That's 12 protons. Now you see with methyl groups there is doublet, you see, right? So it is chance that the carbon which is bearing this methyl group, it will have only one proton. There is a very high chance. This CH3, suppose this is showing 12 hydrogen, they all are showing doublet. That means this hydrogen is there. Okay. So if I consider that all 4 hydrogens are here, all 4 methyl groups attached carbon to this carbon, then this hydrogen will show 12 plus 1 13 multiplet, but it doesn't show that. It shows 2 hydrogen septate. It is possible that this is the group 6 hydrogen, 6 plus 1 7 septate, right? And this 2 hydrogen he was saying, that means there is 2 carbons or 2 hydrogens that are equivalent. And see, this is equivalent structure, right? This is equivalent, this is equivalent, this hydrogen equivalent, all the 4 methyls they are equivalent, and you see you are only left with only one oxygen. That means there must be some ethyl linkage, right? You have to put oxygen somewhere, right? So this is the most possible structure is possible for this compound, which is given here. These 2 methyls are there, this methyl, and here are also 2 methyls, and here is carbon, hydrogen is there. Now you know it to show this mass fragment 102, 87, 45, 43. Okay. Now what will happen? You see 102 is mostly the molecular unpick. C6 H14 O2. Oh, sorry. So 72 plus 14 plus 16. See 102. Now you see 85 one. 85 is only possible. It's only possible. Sorry, 85 not 87. It's only possible if you lose one methyl group, right? You lose one methyl group, you will left with 87. So this fragmentation will produce this methyl will be there. Okay. This will be there, and this methyl is missing. There is a positive charge, right? So this is a fragment. If you miss, if you just remove CH3 15 from this, it will give 77, right? Now you will see the most high intense peak is 45 one. Okay, so what is the best possibility that 45 peak is there? The 45 peak is possibility is that this is broken. Okay, so if this is broken, what will happen? This one peak will be CH3, CH2, okay, and we'll left with CH3, CH3. Here will be a plus, okay, and also if you see here, there will be CH3, CH2O, okay. Now this there is a plus also, so there is a chance that proton it will accept and it will form this kind of thing. Okay, if you calculate this mass C2 H345, how much it is? 12, 14, 24, 16, 45.
43.
It's 45. Now if you calculate this one 15, 15, 30, and this is CH only fragment, not CH2. So for 15, 15, 30, and this is 13. So it's 43. Okay. So most possible fragmentation is this one, where this O bond is cleaved. Okay, and you will left with this structure, that is C double bond OH. Okay. So these are the 4 fragments that I have explained, and these are the fragments you will see, and also this matches with the NMR data. Okay. So anybody have any questions up to this? Okay. So I need to close this session because it's done for today. So in the next assignment, I think we will discuss about this IR spectroscopy. The question will be there. Okay. Okay. Welcome, Sarju.
Sir, how did you get that OH, sir, at last? 45.
Which one?
Last question, sir.
Here.
45 peak molecule.
Which one?
45 peak molecule,
This
C2H5O.
one.
Sir.
Mhm.
That hydrogen near oxygen.
Okay. This one, right? You're talking about?
Yes, sir.
Yes. So if this is not the case, if hydrogen is not there, what do we live with?
O minus.
CH3, CH plus. Okay. This O minus will be there, right?
Yes, sir.
So if this is present and in the solvent, there is, if you know that in the solvent, if you it can take H plus from the solvent. Okay. So O minus cannot leave alone. Okay. So it will take from the solvent. First, it will try to neutralize. Sorry.
Okay, sir.
It will try to first neutralize. If it get neutralized, then if we see that there is a positive charge, so it will try that it will give a lone pair and take the positive charge over it. Okay.
Yes.
Yeah.
Just wanted to have a clarification, sir.
Sure, sure.
There was one question. I don't know whether it is there in the assignment C8H6O3.
E8.
H6O3.
Mm-hmm.
In the earlier class also we have discussed it. A-BB- pattern will be accounting for with a J value of around 8. Hertz will confirm that it is a 1,4 disubstituted aromatic ring.
Right.
I'm assuming that it will be having 2 sets of ortho aromatic protons.
Mm-hmm.
That means it will be 4 hydrogen.
4 hydrogen. Yes.
But one of the assignment it is mentioned as 2 hydrogen only in the same pattern.
Okay. And the coupling constant is same.
Coupling is 8 hertz.
2 hydrogen only.
So that clarification, I don't know how to solve this, because usually
Okay, so
1,4 disubstitution with the A-BB- will be 2 sets of ortho protons accounting for 4 hydrogen. But this question has come with 2 hydrogen protons there.
okay, I got you to question. Actually, what happens? You see somewhere that they usually trying to say you have 2 different types of proton are there. Wherever they say 2H. Okay. So if they ever say they say 4 hydrogen, so these 2 hydrogens they are very close. So you see A prime B prime pattern. So they almost take. I think that they will almost give these 2. They do not give it separately. There is this and this. So this will give 4 hydrogen. 4 hydrogen are there corresponding to these 2 fields. You got my point?
Yeah.
I think they want to give like that.
Maybe this would be giving a chances of having a condensed or a fused ring with an aromatic system.
In which case?
If it is the case, if 2H is actually there, will it be coming out as a fused?
This is possible. Also possible. Para disubstituted means in para position there is something.
That is fine. Yeah. It means even it may have a condensed ring with even third position also could be.
Also, it is possible. Yeah, it's possible.
Okay. Thank you.
Okay. What's your name? MCH Pharmacy?
I'm Rajshekharan.
Sorry?
Raja.
Rajashekharan. Okay.
And I didn't get my assignments not been valued. I'm not getting the scores.
Actually, we don't evaluate these assignments. We are here to just solve some questions. There are you just mail to this NPTEL team. They will tell you.
Okay. Thank you.
Okay, so I think we should stop the recording for today.